Hi, my name is Dennis Angel. I am an XRPL core developer at XRP Labs, and today we're going to be talking about consensus validations. What are consensus validations? The core concept is a central validation management system in the XRPL consensus mechanism. This collects, validates, and manages validation messages from network validators. This also enables a distributed agreement on ledger state across the network. Why is this critical? This resolves disputes between servers about the last closed ledger. It ensures transaction finality through distributed consensus. It maintains trust and consistency across decentralized ledgers. And finally, it provides data structures and logic needed for the consensus process. So what is the validation message structure? Serialized type validation is the core message format. This includes signed statements, which is the cryptographically signed declarations of ledger consensus. The ledger identification contains the ledger hash, the sequence number, and the signing time. This message also includes the validator identity, which includes the public key for authentication, and consensus data, extra information about what this validator is voting on. Why do we use this structure? We use this structure to perform digital signatures to prevent message tampering, temporal ordering, so timestamps enable proper sequencing and freshness validation, unique identification through ledger hashes to ensure precise ledger referencing, and extensibility. The structure allows for additional consensus-related data like amendments. Next, we have timing parameters and network stability. We have the wall clock freshness, local time freshness, early validation window, validation set expiration, and individual validation freshness. Why these specific timeframes? First, for network latency accommodation. This accounts for message propagation delays. Next, we have clock skew tolerance. So this handles minor time differences between servers. We also have stale data prevention, which ensures validations remain relevant and current. And finally, we do this for consensus window management, which balances speed and reliability. Next, what are the core data structures and their roles? The validations template class, which is a generic design parameterized by validation and ledger types. It includes flexible storage and adapts to different validation message formats. It has thread-safe operation, which supports concurrent access, and it includes efficient lookup for optimized data structures. The next one is the ledger tree, which is hierarchical ledger organization. The tree structure organizes ledgers in parent-child relationships. It includes branch support, which tracks the validator's support for each ledger branch. Preferred ledger logic, which determines most supported ledger chain. And memory efficiency for compact representation of ledger relationships. Next, we have the sequence enforcer, which is sequence validation. This provides monotonic ordering, which ensures validation sequences increase properly. This prevents duplication of sequences and blocks replay attacks for duplicate submissions. This allows for pre-validator tracking, which maintains sequence state for each validator. This also includes Byzantine detection, which identifies validators submitting invalid sequences. The reason we have these structures is for scalability, consistency, performance, and security. Next, we will cover the validation lifecycle and its journey. First, we have reception. Validation messages arrive from network peers. We authenticate these messages through cryptographic signature verification. We do a freshness check on the timestamp to validate against our timing parameters we discussed. We have sequence validation using the sequence enforcer to ensure proper ordering. We do trust assessment, which means the validator reputation against the UNL membership. Then we store these validation collections and we check whether or not they are expired. So next we have ledger support and preferred ledger determination. This includes validator weighting, so trusted validators have higher influence. Branch analysis through the ledger tree tracks support for each ledger chain. A threshold logic, which includes minimum support levels required for ledger acceptance. We also have tiebreaker rules, which determine resolution of equal support scenarios. Now we'll discuss preferred ledger selection. The ledger with the most validator backing wins. It must be part of the ledger sequence. Recent validations carry more weight, and this ensures the selected ledger is internally consistent. Why do we do this approach? Because it reflects the will of the trusted validator majority. It automatically resolves competing ledger chains. It prevents minority validators from forcing bad ledgers and provides predictable and consistent ledger selection. In summary, this comprehensive validation system is what makes XRPL reliable, secure, and scalable distributed ledger technology. Thank you for watching.